Hello and welcome to our NGO 500 Capstone project. We are Team 7 and our project is the least squares readjustment of the Canadian primary gravity network. So our team consists of our project manager, Carly, our
Hi.
communications lead, Sebastian, and I am the technical lead and my name is Bryn. So if we get into our project here, um, so this project is the adjustment of the Canadian Gravity Standardization Network, or CGSN. So the last official update to this network was in 1971 based on the standards of the International Gravity uh, Standardization Network, which is now out of date. So it needs to be updated based on absolute gravity observations to conform with the new standard set in 2015, which is the International Gravity Reference System. So this is due to recent advances in technology for gravity measurements. Now that absolute gravity gravimeters are more precise and accessible, more absolute gravimeters are available in the network. So this adjustment is performed using a least squares adjustment, which employs a static adjustment to estimate and adjust the absolute gravity at each station in the network, as well as a kinematic adjustment using observation times to determine instrument scale factor and drift factor, as well as the gravity velocity at each station. This adjustment uses absolute and relative observations. The absolute observations are more precise, however, there are less stations in the network, and these provide the absolute gravity at each station. And then there are relative observations, which serve as ties between stations in the network, allowing it to make up a full network that can be tied into itself. So looking at our data here, we were given a data set that contained 13,118 entries. This included 515 station records, including absolute and relative stations, as well as observations, which included 853 absolute observations and 11,713 relative stations. We went through a data processing phase to remove some local independent networks that did not tie in with the rest of the full network, as well as removing some of the outliers in the observations, which reduced our total number of observations to 13,046, removing just under 100 observations from the dataset.
Okay, so thank you very much, Bryn. So turning that numeric data into a visual representation, you can see pictured on the slide a map of all of our data. So in the blue stars are the actual gravity stations themselves, all 506 of them. And then the red lines are the gravity observations or ties between these stations. So you might notice that around these in some of the areas where you're seeing these gravity stations, some of them appear to be more dense. That is because there are multiple stations layered over each other. Not in real life, but in cities, there are more than one station. There's many that are clustered in groups. And so on a network of this size, to show the whole network, they appear to be overlapping. So it's all representative of the over 12,000 observations that were evaluated, adjusted, and corrected. Okay, so applications of this project. First of all, there's post-glacial rebound. So this is a phenomenon that occurs where tectonic plates rise or rebound after large weight moves are lifted off of them. In this case, it's when glaciers melt or shrink. So when these glaciers melt or shrink, the weight that was pressing these tectonic plates down lifts and these tectonic plates rebound. So the effects of post-glacial rebound affect the whole world, even if the movement is mainly occurring in Canada and other Arctic and Antarctic countries. So this movement is changing the entire shape of the Earth and our geoid, and even more significantly for the average person, it is causing changes in how sea level rise affects the planet. This effect is the main applications focus by our advisors at the Canadian Geodetic Survey as a part of Natural Resources Canada. And so the team also conducted extensive research on the subject. Then, so the eventual goal, as outlined by Bryn, of the IGRS, which is the main reason for our adjustment, is to have a unified global gravity network. So performing the adjustment of the Canadian system and setting it to the new 21st century standards helps build the international gravity network and helps create a unified global network that produces a highly accurate and acceptable datum. It's very important to track changes occurring across our Earth today. All right, I'll pass it off to Sebastian.
All right, thank you. So let's take a look at how our solution works and what it actually produces. So we use a 5-stage process, and the first step is in the data processing, which we took a look at with Bryn when he explained what types of measurements are present and how they are used to establish a reference system. And we looked at what kind of network nodes and tides there are when Carly explained the figure there. So that's the first step. And then the second step is our pre-analysis. So we look to clean our data input files, remove all of the systematic and gross errors, and we will remain with only the random errors, which will go into the adjustment. And in this step, we also apply the reductions of the earth tide correction and the scale factor. And then the third step is the least squares network adjustment. So if you're not familiar with least squares, the objective is to estimate the value of the parameters, in this case, the gravity value, and minimize the sum of the squares of the residuals, which is basically the errors. So it aims to minimize the errors. So in this step, we define our datum and the relationship between the observations and the parameters, which is our functional model, and find our solution for the estimated gravity value. In the fourth step, we take an assessment of the quality of the adjustment by looking at the network precision and reliability and providing a variance component estimation on the residuals. Finally, the fifth step is building on steps 3 and 4 to estimate more parameters. So building on the gravity value to estimate the scale factor, drift factor, and gravity velocity eventually. Okay, so we can look at the results we've achieved. We were able to estimate the gravity value at every station, both absolute and relative stations. And on the left here, we see the residuals that we achieved. So they are within our acceptance criteria of 1 milligauss, except for 3 outliers, which are on the verge of that acceptability region. And then on the right here, we can see that we've got a normal distribution, or even more accurate than a normal distribution, because you can see that large spike at the mean, at the zero mean in the center there. So there's over 5,000 estimated gravity values that are very, very accurate, and very, very many less estimations are less accurate. Okay, so that pretty much wraps up our presentation. If you'd like more information on our project, please join our Zoom room. The ID is here. Just hit the link in the description. Thanks for watching.